Okay, let us progress to our speaker. Marwa Masmoudi, as far as I know, is a PhD student. Is that correct?
Yes.
In Tunisia, and she will be presenting on conditional essential supremum in Riesz spaces. Thank you. Please proceed.
Okay, thank you. So hello, everybody. Before we begin, let me introduce myself. I'm Marwa Masmoudi, a PhD student in the University of Tunis, Tunisia. I want to thank the organizing committee for giving me this opportunity to participate to the conference. Today, I'm going to talk about conditional essential supremum in Riesz spaces. This is a joint work with Youssef Azouzi, Mohamed Amin Ben Omar, and Bersaf Sharif. First of all, I will recall the definition of conditional essential supremum in probability spaces. I will continue by explaining the translation from the setting of probability spaces to the setting of Riesz spaces. Then I will introduce the notion of conditional essential supremum in Riesz spaces and illustrate some properties. To finish, I will introduce the operator delta that will be used to investigate the expression of the distance between an element of L infinity of t and the range of t given a conditional expectation t. And I will conclude by its version in the setting of probability spaces. In the particular case of L2 spaces, conditional expectations are orthogonal projections on L2 of sigma subalgebra. So if you consider a probability space omega fp and a subsigma algebra h of f, the distance of an element of L2 of omega from L2 of h is given by the second norm of f minus the expectation of f given h. Challenged by this result, we might ask whether conditional expectations play similar roles on LP spaces. The answer is negative. So we have to introduce a nonlinear operator to solve our problem. It turns out that the conditional essential supremum introduced by Baron, Cardier-Léger, and Johnson is a good candidate. Moreover, this concept opens a successful approach to extension results in many fields, such as finance and economics. So Baron, Cardier-Léger, and Johnson have defined the conditional essential supremum in a probability space omega fp given a subsigma algebra H as the unique H measurable random variable denoted by M of X given H satisfying the sub on A of X is equal to the sub on A of M of X given H almost surely. The following is an alternative definition which seems to be more suitable in the measure-free framework of Riesz spaces. So the conditional supremum of X given H is the smallest H measurable random variable greater than X. Using this characterization, we obtain easier proofs of many results of the paper of Baron, Cardier-Léger, and Johnson. The conditional essential supremum enjoys many important properties. We cite some of them in the following. Amazing enough, all of these results yields extensions to the setting of Riesz spaces. Moreover, many of the proofs have been revised and shortened. In addition of some contributions made by investigating a few other results dealing with conditional essential supremum in Riesz spaces. So we present here some of the necessary backgrounds, definitions, and results. Q, Labouchagne, and Watson were the first who introduced the conditional expectations on didicant complete Riesz spaces as positive order continuous projections with didicant complete range and mapping the weak order unit E to E. They proved that for any conditional expectation T on E, there exists a larger 3 subspace of the universal completion EU of E called the natural domain of T and denoted by L1 of T, to which T extends uniquely to a conditional expectation. They defined the filtration on didicant complete Riesz spaces as families of conditional expectations satisfying this property. We recall that the universal completion L1 of TU of L1 of T is a universally complete commutative F algebra with identity the weak order unit E of L1 of T. Azouzi and Trabelsi introduced the space L infinity of T as the principal order ideal of L1 of T generated by the weak order unit E. This definition seems to be near to the definition of conditional essential supremum that we will introduce, but only in the case of positive elements. The space of L infinity of T is equipped with the following vector valued norm. They proved also that the product of an element of the range of T and an element of L1 of T belongs to L1 of T. They also showed that the space L infinity of T is an F sub algebra of the universal completion of L1 of T. Let's discuss now the translation from the classical case to the setting of Riesz spaces. There is a correspondence between probability spaces and didicant complete Riesz spaces. Random variables are viewed as elements of the Riesz space E. Events are associated with order projections. Expectations, the role of expectations and the probability measures is played by conditional expectations. The indicator functions are associated with the components of the weak order unit E or the bands. We are now prepared to formulate a measure-free abstract definition of conditional essential supremum in the setting of Riesz spaces. As said before, we choose the characterization to state the version of conditional supremum in Riesz spaces. So if we take a didicant complete Riesz space E with weak order unit E, equipped with a conditional expectation, then the conditional essential supremum of an element of L infinity of T is the smallest element in the range of T greater than F. Similarly, we define the conditional essential infimum of F with respect to T as the greatest element in the range of T smaller than F. The conditional essential supremum enjoys many properties. So the conditional infimum of minus F coincides with the conditional supremum of F. The conditional supremum of the absolute value of F corresponds to the infinity norm given T of F defined by Azouzi and Trabelsi. So if F belongs to the range of T, then F is equal to its conditional supremum and infimum. Big MT and small mt are both impotent and increasing. If we take an element in the range of T which is greater than F, then it's greater also than the conditional supremum of F. Big MT is sub-additive and small mt is super-additive. And they are additive if one of the two elements belongs to the range of T. the conditional supremum behaves very well with supremum, but for infimum, we have just one inequality. The conditional infimum behaves very well with infimum, but for the supremum, we have just one inequality. If we have the particular case where H is in the range of T, then we have those inequalities. We are now prepared to discuss the problem of multiplication under conditional supremum. This problem is likely of fundamental importance since it has not been studied in the classical case. For the class of positive elements in the range of T, we proved that conditional supremum has similar property as the conditional expectation. In fact, we proved that if F belongs to L infinity of T and H belongs to the positive part of R of T, then the conditional supremum of the product of H and F is equal to the product of H and the conditional supremum of F. So what about the general case? We proved that in this case, the conditional supremum of the product is written according to the conditional supremum and infimum of F. In fact, if F is L infinity of T and H belongs to the range of T, then the conditional supremum of the product of H and F is equal to the positive part of H multiplied by the conditional supremum of F minus the negative part of F of H multiplied by the conditional supremum of F. Another question of interest is the link between convexity and conditional supremum. We extended the Johnson's inequality proved by Grobler in the following theorem. If we take a Dedekind complete Riesz space with weak order unit, equip it with a conditional expectation T, and if phi is a convex function from R to R, then for any f in L infinity of T, phi of TF is less or equal than T of phi f, which is less or equal than big M T of phi f. For the first inequality, it have been already proved by Grobler, which is the Johnson inequality. We added the second one using the notion of conditional supremum. Another result relating conditional supremum with convexity is the following. If we take a Dedekind complete Riesz space with weak order unit and phi a convex function from R to R, then for any f in L infinity of T, phi of MT of f is less or equal than MT of phi f. Now I would like to turn to the concept of Maxingales. It's through conditional expectation that martingales are defined. We will work here via conditional supremum to introduce the notion of Maxingales. So if we take a filtration of conditional expectations and Fn element of the range of Tn for each n, the pair Fn Tn is said to be a Maxingale if the supremum given Tn of Fn plus 1 is equal to Fn. Analogously, we define sub-Maxingales and super-Maxingales. The following is the analog of the martingale convergence bounded theorem proved by Q, Labouchine, and Watson, but using the Maxingales instead of martingales. So if we take a super-Maxingale Phi-Ti in a Dedekind complete Riesz space with weak order unit in which the operator Ti are strictly positive, and if there exists an element of the positive, an element J of the G in the positive part of E, which is greater than the absolute value of Fi for all I in N, then Fi is order convergent. At this point, in order to establish the expression of the distance in both probability spaces and Riesz spaces, we need first to define the operator delta. Kaplan has introduced this operator in the framework of the space of continuous functions on a compact X, and has used it and has used it to construct both the Riemann and Lebesgue integral. We will study this operator in Riesz spaces. So if we take a Didicant complete Riesz space with weak order unit equipped with a conditional expectation T, then for any f in L infinity of T, delta of f is the conditional supremum of f minus the conditional infimum of f. The operator delta can be written differently in this way. The operator delta is positive. It's null if and only if f belongs to the range of T, minus f and f has the same delta. Then if G belongs to the range of T, then delta of f plus J plus G f. The following is a preparatory lemma to our main result. So if we take a Didicant complete Riesz space with weak order unit equipped with a conditional expectation E, then for any f in L infinity of T, those inequalities hold. As a consequence of the previous lemma, we prove that the operator delta is non-continuous. We now have assembled all the concepts that are needed to formulate our main result. So in a Didicant complete Riesz space with weak order unit equipped with a conditional expectation T, the distance of an element f in L infinity of T from the range of T is equal to the half of delta of f, and this distance is attained. So once we moved on from probability to Riesz spaces by generalizing many results and then producing new ones, we come back now to the classical case and formulate the previous theorem in the probability setting. We obtain a very nice new result. So if we consider a probability space omega fp and a sub-sigma algebra H of f, then for any x in L infinity of omega, the distance between x and the elements of L0 of H is equal to the half of the infinity norm of delta of x, and this distance is attained. Thank you for your attention, and here are some references.
Thank you, Marwa. Are there questions? Oh, I have a question.
Yes.
Do you have decomposition theorem, like the Doob decomposition for your Maxingales, for sub and super Maxingales in terms of Maxingales? And what would they look like?
I think it's a good question, but we don't study it.
I'm sure you can do the decomposition.
We can think about it, yes.
Are there other questions from the audience? No other question. Surely there's another question. So when you take your Maxingales from Riesz spaces back to an LP space, do you get more out of it than you would have from the classical theory, or do you get back just exactly what you got from the classical theory?
Can you repeat your question, please?
If you've done now work on you've extended Maxingales to the Riesz space setting. Now,
Okay.
if you take your Riesz space as, let's say, an LP space, and you can take a slightly larger LP space like your T universal completion of it or something like that, what do your results give you back in the classical measure setting? You will get some small gain, certainly, from working in Riesz spaces when you apply it back to the measure setting. You'll get an extension to the maximal setting where you can work out conditional expectations. At least that much you will get, which is beyond the classical setting. You'll be working in larger spaces than L1.
Yes.
So have you done the application to see exactly what you can extract in the L1 space setting, for instance, or generalized L1? It would be interesting because you will gain some extra mileage beyond what is in the classical literature.
Yes.
Anyway, that's just an idea for later on. Okay.
Yes, thank you. I will see.
Sorry, please proceed.
I will see it.
Okay. We thank our speaker, Marwa. Thank you again. And the next speaker